this on? Cool.
Okay. So now Chris will tell us about locality-sensitive hashing.
Okay. Thank you. So this is a joint work with my advisor, Rachel Ward, and we're just talking about this fast algorithm for LSH. So what is LSH? So the goal of LSH is to solve the nearest neighbors problem. So we're given a point set of n points, and we query some point from our set, and we find it's either exact or approximate nearest neighbors. And the problem is that in very high dimensions, nearest neighbor search, exact nearest neighbor search, is essentially degrading to just the brute force algorithm. So I just look at all of the pairwise distances with every other point. So in order to sort of get over this bound, what we have to do is we have to relax to an approximate nearest neighbors. So this is saying, I look at my closest point, and I want to find some point within a multiplicative distance factor of c. And the way we deal with this is locality-sensitive hashing. So basically, instead of directly observing the distances, I'm going to hash my points randomly into buckets so that close points get hashed to the same bucket, and far points get hashed to different buckets. Okay, so the algorithm is specified by the hash family. So this is a random hash family. And if P1 is a lower bound on the collision probability at distance r, so we want this to be very large. And if P2 is an upper bound of the probability of collision at distance greater than c of r, c times r, so we want this to be very small. And then the quantity we're sort of interested in is the sensitivity of the scheme. And why is it that? So this rho factor that is given by that equation determines how fast our query time is. In particular, our query time scales something like n to the rho. So for the case rho equals 1, we get exact search, because that's just brute force algorithm. So we want rho to be much less than 1. And so we see that in d-dimensional Euclidean space, which is our setting, sort of the optimal lower bound is 1 over c squared asymptotically. And here, if you recall, c is sort of the amount of multiplicative distance we were allowing in our approximate nearest neighbors queries. Okay. Does that make sense, the problems? Okay, so in particular, we're considering angular distance, which is Euclidean distance on the sphere. Just to mention two previous algorithms, so spherical LSH does achieve this optimal asymptotic sensitivity, but it's very difficult to compute in practice. And then hyperplane LSH is very simple and easy to implement, but it does not achieve this optimal sensitivity. So what can we do? So instead of those two schemes, what we have is Cross-Polytope LSH. And this is nice because it's simple, and it also achieves the optimal bounds. So what are we doing? We take our query point, and we're going to rotate it randomly on the sphere, uniformly at random. And then we're going to round to the nearest vertex in the cross-polytope. So this is all of the plus or minus coordinate axes. And what's the deal? So the deal is that the sensitivity factor is converging to this 1 over c squared at the correct rate. It has comparable empirical performance to hyperplane LSH. And so the bottleneck is really in the pre-processing time to hash, because this sort of dense Gaussian rotation matrix takes O of d squared time. And that's really what we're trying to improve. So what's the idea? Oh, and just to mention, so this paper by Andoni and Dick, Larhoven, and Regenstein, they found that this really strange rotation matrix, so this is a pseudo-random rotation matrix. It's not really, but it seems to work in the case of cross-polytope LSH. So what I have is a Hadamard matrix, a diagonal Rademacher matrix, a Hadamard matrix, another independent copy of that Rademacher matrix. And I do this 3 times, and somehow this works. Kind of mysteriously, if you do it 2 times, it doesn't work. I know. And this was not really understood until this paper in 2016. And here they proved it actually works, but for a sort of restricted range of angles. And if you're curious about that, I can tell you afterwards how they did that. And of course, this is faster. This is time d log d. Okay, so what's our idea? So I want to replace this dense Gaussian matrix with a low-rank outer product of these short fat matrices. So here, G1 is essentially a Johnson-Lindenstrauss transform. So it's going to project from dimension D to order log D with very low distortion. And now, basically, we treat our vector in this log D dimension as this sparse vector. And we're just going to apply a full rotation to the sparse vector. But that takes time d log D. And the moral of the story is, if I'm projecting down to this low dimension and I have pretty low distortion, everything should work out appropriately. And it does. So if we recall that the sensitivity factor is what we want to minimize, in the case of fast cross-polytope LSH, we actually get the optimal convergence to this 1/c² factor. And so little is lost by using fast approximate rotations. So this is nice. And then we take it one step further. So we kind of tried to minimize the amount of randomness. So if you go back to this scheme, this has order d bits of randomness from each of the diagonal Rademacher matrices. And we were kind of interested if we could lower this even further to order logs d. And in fact, you can. So I'd say the key technical result we use is this JL transform by Kane and Nelson that only uses order of logs d bits. It's quite technical, but it's really an amazing result. And then so this is the projection step. And then for the Gaussian step, it turns out it suffices just to discretize your Gaussian matrix. And this will actually still maintain the correct asymptotic row, but maybe its order of convergence is not quite correct. It's a little O of 1, but we still get what we want. OK. And then just to mention some recent work and some future directions. So our scheme is kind of oblivious to our data set because it's just rotating and rounding. If you want to sort of use properties of your data set, maybe it's, there's points that are concentrated more in this area. You can sort of intelligently create hashing schemes that exploit the structure of your data set. And these can actually perform better than the theoretical lower bounds in LSH. And also if you're concerned with time-space trade-off. So I didn't mention space, but for LSH, it scales something like n to the 1 plus rho. So the question is, can I get this sublinear in n and still maintain the sublinear query time? And recently, it was found that this is also possible. And then I just think an interesting remaining question is to show the sort of usefulness of this HD matrix for a full range of angles. Yeah. Any questions?